Time to begin for us. So, good morning and welcome, everyone. Thank you for coming to this talk. My name is Adam Furmanek, and today we are going to talk a little about async. Very hot topic recently, like for the last decade in C#, obviously. But today, what we are going to do is we will see it from a different angle. We'll see whether async in C# was implemented in the right way, whether the way it was implemented allowed us to actually gain the most of the performance and all the benefits we could get, and if there are any drawbacks to the implementation we have in C#, and especially in the light of the project Loom in Java, which was released quite recently, and which turned the table significantly. So this is what we are going to do for the next hour. We'll discuss how async is implemented, what the pros and cons are, and how to re-implement it using different approach, namely fibers, as you can see. We'll learn what fibers are, how they can be used in Windows, and whether it's possible to get some other benefits from this implementation. Before we move on, a couple words about me. I'm a software engineer for over a decade now. I've written also 2 technical books, one about .NET, one about applied maths, especially integer linear programming and how it can be used in programming. I'm also an author of Random IT Utensils blog at blog.adamfurmanek.pl. I encourage you to take a look if you are interested in things like this. And also drop me a line or email, Twitter, whatever works for you, so you can reach out to me after this talk. If you had any questions, feel free to ask them anytime. Feel free to interrupt, or so you can wait until the very end. We'll cover all of that. Okay, moving on. The agenda for today's talk is, first, we'll try to understand why was async introduced in the beginning. Why was it useful? What it tried to solve, and we'll see whether it solved it or not. Then we'll learn some other concepts in software engineering, like operating system level threads, green threads, coroutines, call.cc, and other stuff which can be used to structure our applications a little differently. And ultimately, at the very end, we'll just go to the demos showing you how we could implement async in different approach. The similar approach that Java took on, which is way different than what other languages are doing. So the first thing, why async? Probably you know that since the very early days of .NET development, we always had this need to be able to execute some code like outside of the main execution flow. We always wanted to run something in background, calculate something on the side. So that's why we wanted to have this ability to get a part of this code and just run it somewhere else in some different way without actually paying attention to all those little nasty details, how those things are executed. And the first thing we could use to do that was Asynchronous Programming Model, APM for short. So we had this pattern in C# language, which was based on 2 methods, one of them named begin something, and the counterpart named end something, which allowed us to execute the calculation on some other thread, context, something else. We didn't need to think about how it was executed, but generally it was executed somewhere. The idea was that we just triggered the operation, and then when we want to utilize the result, we have this end method, which either gives us the result if it's already available, or it blocks until we get the result. We also had to provide this lambda, which would do the continuation part. So when the result is done, do this thing. So that was the first pattern. The second pattern we could use was EAP, event-based asynchronous programming model, which was based on the idea that we have this background worker where we can submit our jobs to be executed, the piece of code we want to run, and it was triggered, executed on this background thingy, and then we had the continuation used in a way of attaching a callback. So we had a callback which we could attach to the worker when the thing to execute, to calculate was finished. We had this callback being triggered, so executed by the platform. So that's yet another approach we had. Obviously, it could be configured, canceled, and all that stuff we would expect from like a decent mechanism to support. The problem with that was, with both mechanisms, was that they did not necessarily allow us to structure the code in the linear way. Like both here in this EAP, we had to provide this callback. Similarly, here in this end read thingy, we also had those callbacks which were executed when things were done. What we wanted to do instead, we wanted to have a continuation wrapped as a first-class citizen, as an object which we could just carry around, pass from one method to the other, which would encapsulate everything which is to be done. Not only the code, but also the parameters, all the continuations, security features like user ID, impersonation, whatever reliability, context, whatever else, whatever you imagine, right? All those had to be captured in one single object, which was task, which we could just carry around. So that's how TAP, task-based asynchronous pattern, started. And we had this idea that we want to create one single task which allows us to encapsulate the logic, and then we could wrap them together with the powerful continue with method. Typically, the way we used it was that we just added continue with and provided yet another lambda. However, there were multiple different parameters, like to continue only if there was an exception, or if there were no exceptions, or continue on different tasks. Scheduler, different thread pool, whatever else, multiple different things. If you are interested more in details how this thing was constructed, etc., I encourage you to take a look at my talk, which is Internals of Async. You can find it on YouTube, and you will learn all about that stuff. So this is what TAP gave us. And also, nice part about TAP was it was super simple to actually make it parallel. It was super straightforward to run it on multiple threads thanks to peeling. What we had to do is just do dot as parallel, and then bang, all the magical functions we could use with link were executed like in parallel. Obviously, .NET did quite a lot of scaffolding under the hood, also calculating whether it's worth running things on multiple threads or whether they should still go on single-threaded model, whatever else. It was taken care of by the platform. The only thing we had to do was as parallel, and we were all good. So that was the idea. The problem with this approach was that, hey, we are still wrapping those things in tasks. We still have those tasks flying around from left to right, and we need to use this continue with method where we just need to provide this yet another lambda, which still allows us to go more or less like linearly, but still we have those details exposed. So that's why async and await came to the game. And there was one more super important thing why async and await was introduced. It was to allow us to write the code which does not block the operating system level threat. We'll get to that a little later. However, before getting to those details, let's see a little like funny remarks about async and await. First thing is, you can await anything which is awaitable. It means it's very similar to the for each loop. You do not need to have any IEnumerable, IWhateverator on top of the collection you'd like to enumerate over. The only thing you need to do is you need to use the duck typing. If the collection gives you the move next and the current, then you can do for each over it. There is no interface needed. Same thing applies to async and await. You need to use the duck typing to, and if you have a type which is called awaitable, meaning that it gives you this method called getAwaiter, which returns you a type which allows you to check whether the result is available or to continue on when the result appears, then you can await on anything, meaning that we can actually await on any integer. So let's go to a very first simple demo. So what we are doing is we are trying to await an integer. So you can see that first thingy, we do have some code which slept for like 2 seconds, okay? And the thing which is happening under the hood is we are just calling await 2000. So we are awaiting 2000 milliseconds. How's that possible? The only thing you need to do is you provide an extension method and you extend the integer type to return the awaitable type. So it does have the method called getAwaiter, which returns you any awaitable type, and under the hood we are just doing task delay and returning the same thingy which task delay would return. So when we call this await 2000, what it does under the hood is it calls integer getAwaiter, so it finds the extension method we have below, it gives the code the awaitable type, and we can just wait for it. Obviously, I'm not suggesting that you should go and rewrite all your integers to be awaitable in your code base, but this gives you the idea that, hey, anything can be awaitable. And that's the power of the async and await, that you can use it with basically anything you'd like to go with. So that's the thing. That's the first thing. We also know that async and await gives us this ability to basically write the code like linearly, right? We don't need to think about attaching continuations. We just do await, bang, we are good. That's what documentation tells us, right? There are tons of problems with that. And again, I refer you to yet another talk, which is called like, why async is the worst idea in C#. You can find it on YouTube, obviously. But what we are going to do to focus on today is the third part of the async, which is asynchronous code does not block the operating system level thread. And this, like, very simple sentence actually gives us a lot of useful information. First, we cannot block. That's the important thingy. But what is even more important here is we cannot block the operating system level thread. Meaning that with async and await, we can actually block, but not on the OS thread. And this is what we are going to utilize under the hood. We will see how the blocking is implemented currently in C#, and then we will see how it could be implemented in different way. So this is what's up next. And in order to get all of that, we need to go through all those like 3 big deals of async and await in C#. So the first big deal is async in C# is implemented as a coroutine compiler level transformation. That's a very magical term, which we'll see later on, but which tells us that whenever you write a method which is marked as async, compiler steps in and rewrites this method into the state machine. So we'll get that a little later. Also, similar thing was happening with yield keyword. Compiler was basically restructuring all your methods to provide this coroutine-like experience. The second part is C#, async in C# is implemented as a service locator for promise orchestration, meaning that there is a static global variable named synchronization context, which gives you like the service locator behavior into how you schedule the continuations. Because depending on what application you run, if it's like a desktop application, or if it's like a web application, or if it's a Blazor thingy, then your continuations need to be scheduled differently. In desktop applications, they can go on one thread only, because whenever you await on the user interface, the callback needs to be executed on the same thread which manages your UI. Why is that? Because otherwise it would have no access to the UI components, buttons, labels, etc. You would get exception that you are trying to access the UI from some other thread. However, in the web world, the only thing we need to take off is that the continuation needs to be executed in the context of the same web request. You do not need to care whether it's exactly the same thread, operating system level thread, but you only want to, the only thing you want to care about is that it's inquired in the same web request. So you have access to the same like request headers, response headers, whatever. Similarly, in Blazor, because we are running in JavaScript mode, then we need to inject everything into the JavaScript like this one single thread pumping mechanism. So this is why the synchronization context needs to take care of that. And hands up if you ever heard about synchronization context. There are a couple of hands, that's great. For all of you who never heard about that, that's the power of async and await. That is a service locator which you do not need to even think about. However, it gives you tons of issues if you are trying to go with like multiple threads when it's expecting single level threads, so then you have deadlocks and all that stuff. Again, referring you to some other sources, but generally it can become nasty. And the third part of async in C# is that it has statically bound promise factories. What does it tell us? The task type, which we use in C#, is known in multiple different languages like a promise, like future. Depending on which language you're using, you have different nomenclature, right? But the thing is, it has the statically bound promise factories, meaning that you need to have a factory creating you this promise. And in C#, it's statically bound because you specify the type which is returned from the method. You always need to specify that it's what? It's a task. But at some point, .NET Platform or .NET team realized that, hey, tasks are very heavy, they are garbage collected, and they have all the drawbacks of being like regular GC managed objects. So let's introduce something which is passed via stack. So what happened? We had to rewrite all our functions from task to value task, right? Again, that's a nasty issue with async because, hey, it's statically bound. So during this talk, we'll address all those three big pieces of async and await and see if we can do better. So let's move on. The async. Important thing about async. The mechanism which was introduced in C# was actually one of the first mechanisms out there in the enterprise world. It influenced multiple other languages. Obviously, there were other like some niche languages which did support things like that, but C# was the first big one to support those. And it influenced others. For instance, Haskell, Python, JavaScript, TypeScript, etc. All of them implemented async and await basically in the same way, meaning that there was this coroutine transformation, there was some service locator for orchestrating continuations, and there was some well-known type, either like more directly exposed or hidden via duck typing, whatever else, but generally there was this type which supported the asynchronous programming. However, it does not need to be implemented this way. And when I was preparing this talk for the first time, it was before Java 17 was released, which was a couple years back, and they were working on a different approach, which was called Project Loom. Now this Project Loom was already released, so what I'm going to show you is conceptually equivalent to what they are doing in Java. So now they have their own async and await, and it will work the way I'm going to show you today. Obviously, they implemented it with their own platform, yada yada, but generally conceptually indifferent. And I was always saying that, well, we don't know which approach is better when it comes to performance, usability, etc. We still do not know that because Java released it quite recently, so we do not have all the data points. However, we already see that their approach may be way more efficient. For instance, now there was a very interesting example released like literally a couple days ago that a guy implemented a method or an application which is able to handle 50 million concurrent connections on one single box. This is something we cannot do with C#. If you ever heard about C10K problem or the challenge to handle 10,000 concurrent connections on one single machine, this guy made a big step forward to see 50 million concurrent connections. So generally, the thing is that this different approach may be way better in terms of performance, but we'll actually see that in like 5 years from now, because we didn't know how it will perform, how it will behave. The same, we didn't know about async and await in C#. Now, like a decade later, we already know that C#'s implementation has tons of various problems when it comes to deadlocking, when it comes to rewriting the code, colorful functions, but we generally know it's beneficial. We don't know yet whether Java's approach is better. We'll get to know that in a couple of years. Moving on, in order to understand all those three big pieces, we'll need to go through some theory. So let's dwell into operating system level thread and what else we can use to implement asynchronous programming. So the native thread. The first thing we need to know is whenever we actually execute something, at the very bottom of the runtime execution platform, there is a thing which is provided by the operating system, which is a native thread. So this is the thread you create with your Win API or pthreads or whatever else. It's basically a thread, so a piece of machinery which allows you to run a task, something which is written or named by the CPU architecture as a task. So there are two different types of threads, foreground and background threads. They need to have the stack, so memory allocated for the stack. In Windows, when we are talking about like Windows 10 or Windows 11 64-bit, a typical application or a typical thread has three different stacks. One for kernel space, one for user space, and one for the Windows on Windows 64 execution mechanism. And taking into account that by default, user space stack consumes around 1 megabyte of memory, which may or may not be committed like from the very beginning, but typically it may be, means that whenever you create a new thread, it allocates 1 megabyte of memory. So that's why they are telling you, hey, do not create threads by hand, because if you try to create 50 millions of them to handle 50 millions concurrent connections, you would have quite a lot of memory consumed, right, for doing nothing yet. Important thing, Windows, and the same goes for Linux, generally anything running on x86 architecture, schedules threads, not processes, meaning that the thread has its own priority and its own time slice, and it's scheduled by the operating system. On top of that, .NET Platform gives you the managed thread. So it takes the native thread and wraps it into the system threading.thread class, which handles the operating system level thread, gives you quite a couple of interesting features, like you can name a thread, you can attach an ID to that. So if you are dumping a memory and then analyzing your memory dumps, then you can see the names of the threads. So generally, whenever you create a new thread, always give it a name, to it. So then when you are trying to like debug memory dumps, you see what this thread was supposed to be doing and not only what it's doing. Generally, it pre-commits the stack when a thread is created, meaning that whenever you create a new thread in .NET, it does allocate the memory for you. And also, if you have an unhandled exception on a thread, it kills your application. So generally, whenever you create a thread, always do try catch everything, so your application doesn't die, give it a name, and then let it go. So this is what we have at the very bottom. Now, the concept of operating system level thread is very useful for us because, well, everything in user space needs to use some kind of threading machinery. However, nothing stops us from reimplementing threads in like the user space. So what we do is we can create our own threads running entirely in .NET, entirely in C#, and not being run and managed by the operating system level thread. And those are called green threads. The name green actually comes from Java again, because Java started with their own implementation on threads, and it was developed by the green team in Sun Microsystems. So that's why they called them green threads, and the name stayed around for a little longer. So that's why we are calling them green threads. The thing about green threads is they are not scheduled by the OS. Just like a couple slides back, I told you that Windows schedule threads. This is different here. It's not Windows which schedules threads, but it's the runtime platform. So it would be .NET, JVM, JavaScript, V8 engine, whatever you name. And now the important thing about that is you need to run those threads on top of something. So now you have the idea of mapping your green threads to operating system level threads. So you can go with multiple different mappings. You can go with direct mapping one-to-one, so one green thread is one OS thread, or you could go with multiple threads going to a single OS thread, or any way you wish. So your threads can migrate, can carry their state in between different OS threads, etc. So generally, we can reimplement anything. The important part is we need to take care of everything when we are doing that. So that's why most platforms do not want to do that, but nothing stops us from doing so. The advantages are, first, if we are taking care of creating those threads, this can be way faster because we do not need to switch to the kernel thread and the user space, kernel space, user space back and forth, right? We can do all the scheduling directly in the user space, which can be faster. So depending on which implementation you use, you may actually see some performance gains with green threads. However, there are also issues with that. Because we are just running those green threads on top of native threads, you cannot use actually multiple processors depending on which scheme you have. If you're mapping like n threads to a single OS thread, then at some point in time, only one green thread can be executed, right? Because you are mapping to one OS thread. You cannot get true parallelism with this approach, with this mapping. You need to go with something slightly more clever, but generally the outcome is you cannot get the full parallelism with this way. Also, when it comes to the I/O operations, we have this drawback that whenever we have n threads which needs to be executed by your runtime, when a thread gets blocked, for instance, because you did file read all text and you are waiting for the data to arrive, then effectively all those n threads are being blocked. Why? Because your operating system level thread is suspended, waiting for the data. So whenever you go with this approach, you always need to go with asynchronous operations all the way down. Otherwise, you have issues and you cannot get the performance. But that's the idea. There are obviously different variations of this concept, depending on the language, like Erlang uses green processors because they do not share the memory. It's generally, Julia uses something different, Python uses tasks. Generally, it's the same concept, but there are details in implementation. Moving on. So we have operating system level threads. On top of them, we could build green threads. What would green threads give us? The idea is that we can assign work to different green threads, and whenever we want to await something, we can switch to a different green thread, right? And operating system does not need to know about that. But we could take a different approach. We can go with a thing called coroutines. Instead of having a method which allows us just to be executed like once from the very beginning to the very end when there is the return keyword, what we can do instead is we can come up with a method which can be suspended and resumed, and a method which can return a value multiple times. And this is called coroutine. So generally, a single routine is basically a very specific case of coroutine which returns just once. Meaning that when we have a coroutine can decide when it wants to return a value. And the question is, how can that be useful for us? And the answer is, what we do have in C# is the yield keyword. And this is basically a coroutine. What we do have is we have a for loop counting from 0 to whatever, and we do want to return multiple values. So we do yield return. It returns multiple values, as you can see. Whenever you call yield return, this method is suspended. You can take the value, use it, and then when someone wants to get another value, it resumes the method and waits for another value. Now the question is, how is that implemented under the hood? And a couple slides back, I told you that compiler uses coroutine transformation. And this is exactly the place where the coroutine transformation happens. So when we have a method like from the slide which we've seen, which is just for loop returning value, this is what compiler creates for you under the hood. It creates the class which has a method getCounter returning you IEnumerator, and what it does next is it creates a very nasty class generated by the compiler, which holds things like state, current value, and all that stuff, and provides a method which is called moveNext, which does all the heavy lifting. So whenever you call this method, if you see how the compiler generates the code for you, like the caller of this method calls getCounter and gets the IEnumerator class, IEnumerator instance, and then repeatedly calls moveNext method on top of that. And this moveNext method, it knows where it is, and it reworks this whole for each loop, the for loop here. It reworks all the exception handling, all the stuff, and just knows where to carry on from after you get the value. So you call moveNext, it calculates the next value, returns this value, which you can later get using the current property, and this is how you operate. You get the IEnumerator from here, you call moveNext, it tells you, hey, I do have another value, returns you true, then you go to current, get the value, then you call moveNext again, and so on. This is what is happening with the yield keyword. And interestingly enough, the same thingy is happening with async and await, but we'll get to that in a sec. So drawbacks of this idea, of this approach is they introduce the so-called function coloring. Whenever we have this yield return, we cannot just go with method returning integer, right? We need to return IEnumerator of integer, right? Or IEnumerable of integer. We cannot go with just a single value. We always need to go with the collection. So this is called function coloring. We have colorless functions, which can return anything. And we have colored functions, which can return anything wrapped inside the collection, inside the IEnumerable. So the problem with that is those methods cannot necessarily be used in like void contexts, right? You cannot await your method in a constructor, right? because if you do await it, then you would need to call await on the method. However, then you would need to return a task from the constructor. But you cannot return a task from the constructor because you are just returning the instance. So that's one problem. The other problem is, well, your async methods, they generally cannot return void. I mean, technically it's possible, but gives you so many problems that better not do that. But generally, this is something we can't do in all the contexts we would like to do. Also, when it comes to exception handling, they change a lot. They also increase the memory allocation because we need to create the intermediate collections, etc. Generally, multiple problems, even though this gives us quite a lot of benefits. Now, how does it work with async? If we take a method like this, and we have console write line, await, yada, yada, what the compiler does under the hood is, first, it creates you this our async method. So we start with our async method here, and we have a series of print lines and awaits. So it gives you this method which looks very like straightforward, right? But what it does under the hood, it utilizes again some compiler generated type, which does all the heavy lifting. Again, we have the move next method, which handles all the different states, which does the switch case, which breaks, which jumps around. You can see even go to here. So generally nesty code, and it awaits all the stuff, returns you all these things. So this is the code which is generated 130 lines for this single method. So this is the coroutine transformation done for you by the C# compiler. The important thing is that this C# compiler transformation is like transparent for the .NET platform. Meaning that's the advantage of async. Your .NET platform does not need to know anything about asynchronous code because compiler does the heavy lifting. So this is why it's way simpler to implement, because you can just do it in the compiler. You don't need to have any runtime support nor the operating system support. Okay, so that's yet another approach. Now, when it comes to a different thing we could do, is we can go with a thing which is called continuation passing style. Instead of writing a method which gives us a value, we can write a method which gives the value to the continuation and calls the continuation. Sounds tricky, but generally is rather straightforward. Let's see this in action. Let's say that we would like to calculate a Fibonacci number. So the regular implementation would be, hey, give me a Fibonacci of n. So n Fibonacci number, right? What we do is some black magic with switch case and then returning the Fibonacci. But ultimately what we do is we just return the value, okay? This is what we do. We return the value. So whenever we want to print this value, what we do is we calculate, we call the Fibonacci method here, and then this value which is being returned is actually passed to this point, okay? Because we get the value and then pass it through. With CPS, what we do is we ask the method to continue for us. So that's the difference. This method now not only gets the parameter, hey, which Fibonacci you would like to calculate, but also what would you like to do next? So this is the CPS, continuation passing style. And the difference is we call the Fibonacci, passing it the parameter, we want the 10th Fibonacci number, and we also ask the method, hey, when you are done, do not get back to me, do not give me the result. What you should do instead is just call this code, call this lambda. So this is the CPS, and you can obviously see this approach with the task wrapper, right? Task continue with, when you are done, don't give me the result, but go with this continuation. What does this give us? Well, this approach, if we bend our minds a little more, this allows us to implement a thing which is called call CC, call with current continuation. So what this allows us is we can actually turn the things inside out to implement any construction instruction controls we would like to have, for instance, to implement like the break, return, or whatever else. And now, how would the call with CC, call with current continuation, look like in C#? So let's say that we have a regular method which accepts the continuation, okay? And what we do in this foo method is we first call this continuation passing it number 2 or value 2, and then we return 3, and ultimately we print the value returned by the function. So this is a regular C#, so this returns 3, right? Like the continuation here, which is passed here, is basically the empty lambda, so it doesn't matter. Okay, but now if we had call with CC in C#, what we would do is we could call CC, sorry for that, we could call CC foo this way. So then the compiler, what it would do, or the runtime what it would do, is it would take everything following the foo execution. So everything following the foo execution is probably a thing like this one. So then this thingy is ultimately wrapped into a lambda continuation, which is then passed as this bar. Okay? So now when foo calls the bar continuation, so when we call bar with number 2, what happens next is the foo is being terminated and we continue with the continuation, and the continuation is this thingy. So the console write line. So then it prints 2. So this is the pattern which we can take, and this is exactly like async and await is yet another way of using this pattern, even in a very narrow context. We just want to await the thingy and then continue with it, but this is what the compiler does for us. So this is when it comes to CPS, green threads, and all that stuff. And now, to get it a little more usable for us, what we need to use is, there is a thingy, there is a question, I believe, right? Yeah. That's a made-up syntax because C# does not support call with current continuation. This is how it could look like in C#. How you would call with parameters? Probably parentheses and etc. Cool. Moving on then. So fibers. We already covered operating system level threads. We covered green threads. Now, Windows provides you a thing which is called a fiber. That's a green level thread implemented by the Win API. The idea with fiber is that basically it's a thread which is cooperatively multitasked, meaning that a thread asks to be rescheduled. So similarly to what we have with coroutines, you need to have async, you have to have an await keyword or yield return keyword to indicate where you want to switch the context. So this is the cooperative multitasking, but it's implemented by the Win API. So the problem of this approach is that gives you a significant memory usage because it's implemented in the Windows API, so in the kernel mode. So it cannot use, like it doesn't give you all the performance benefits. However, it also has this drawback of, because it's a green level thread, when you have multiple fibers, you need to use the asynchronous programming model to do at the I/O. Otherwise, you block all the fibers and you cannot get the performance. And you cannot use all the things for locking, etc. But generally, this allows us to implement the green thread approach, like super simple, because we have it already exposed. So what do we need to do? Imagine that we now want to implement async, knowing all the things about green level threads, about the continuation passing style, about the coroutines. We want to use fibers, so the green level threads, to implement async. How do we need to do that? Technically, we need to call a couple of Win API methods to convert a thread to fiber, and then we can use switch to fiber to switch between threads. How do we do that to do async? This is the next part of this talk. So let's see what we are going to do. Let's close this one. Let's start with the regular async example and see what we are doing. So let's start this up first. The important thing about async, as I mentioned, is that we cannot block the operating system level thread. That's the crucial point of asynchronous programming. If at any point of time we block the OS thread, then there is no use in async at all. What we are doing is, we'll have a demo, an example code, which we'll use multiple times throughout the demo to show you what we are tweaking with. So first thing we are doing is we want to execute two tasks, like in parallel, concurrently, side by side. First of them is run internal, and then we have some interjected side job. They don't do anything special. Run internal is just calling run internal nested, which sleeps for 2 seconds, awaits the sleep, returns some data, yada, yada. Nothing special, okay? Important part is it waits. It takes some time for it to finish because it needs to block on something. And then we are just awaiting this, okay? So we are sleeping for 2 seconds. That's the important part. The second important part is we are running a side job. So in the time when we are sleeping, we would like this side job to be executed. And this side job does nothing, it just prints. okay? So what we want to see in all the examples is we want to have this output that we are running there's some nesting inside this regular job, and then somewhere in between we have our side job interjected, okay? You can see that we are effectively sleeping for 2 seconds, so this side job is executed in is like 2 seconds, which we can use to do anything, and then the continuation finishes, okay? So that's the idea. So this is the regular async and await code you would be implementing with all the coroutine transformation, etc. Now, how can we do exactly the same with yield keyword? The important thing is that yield keyword, which was there like a couple years back before async and await, allows us to do exactly the same. So now we are going to reimplement async and await with yield keyword. So first thing we'll need to do is we'll need to have some bookkeeping which is done for you by the .NET platform. So whenever you do async, you use async and await, when you await something, there is this continuation which is pushed on the synchronization context, which is basically put into some queue. And then the thread observes the queue. If there is a new message in the queue, meaning that, hey, you need to do some more work, it takes the message from the queue, does the work, and carry on. Okay, so that's the idea. We need to re-implement this part. So what we have is we have dictionaries of all the jobs we'd like to be doing, some semaphore for synchronizing on top of the queue, and then we also have the enumerator. So this is a kind of the regular enumerator you have in C#, but with flag whether there is some work more to be done, and the idea is we'll stack those enumerators on top of the other. So whenever you do want to now we want to bend our minds, and instead of doing await on a method, we want to do yield return on a method. And the thing is that the method which we are yield returning, it can also await inside, so it can also do yield return. So when we are doing yield returns, we need to return collections, right? So before continuing with returning the external collection, we need to return the internal collection which was there. So when we are doing yield return, we need to understand there was this stack of enumerators built on top of each other, and this is why we have the enumerator with flag to basically build this stack of thingies. What we do is we have the move next method in this enumerator, which basically checks, hey, if I was already done, then I'm done. Otherwise, I get the enumerator which was there, and I call move next in it. If we've seen this move next method with the for loop, for instance, we are basically calculating next integer, right? If there is nothing which we calculated, then we try like unstacking the thing. We check whether we were stacked enumerator and we remove it from the top of the stack, or we can obviously push something more on the stack. We'll see that in how we are going to implement the run internal. So this is the same thing which we had with async and await. So now what we are doing is we are calling the run internal nested, we are getting its enumerator and marking it, hey, you go ahead, do your work. And then instead of doing await, we can do yield return, okay? And this thing, this run internal nested, is yet another thingy which returns us the IEnumerable something instead of task. And again, when we want to wait for it, we just do yield return. And because we are mixing this with tasks around, then we have some magic wait, which is not important. The general idea is instead of using await, we do the yield return. So the way we do it is we have a run method. So the main thread, which has those queues of the things to be executed, okay? So what we do is we loop through this queue, we get the thingy from this queue, and while there is something to be done, we just get it and call the move next method from the enumerator. And if there is something new to be scheduled, new continuation, then this new continuation is pushed into this queue again. So this is how we implement it. And if we are all done, then we just break. Nothing important here. So the important or the interesting part about that, let me just check. Yeah, this compiled correctly. You can see that, hey, with this approach, we can also get exactly the same thingy. So we are now running with generators instead of the async and await. We can get the side job being interjected somewhere in between, and we can get this 2 seconds delay. And this is actually something people were implementing before async and await was introduced to the C#. You can go look over Stack Overflow and you'll find people asking, how do I use yield to implement async and await? And they were doing that. So this is something you can implement by hand. And this is the way it's implemented under the hood. Like all this queuing, all this scheduling is done for you. And now we enter a slightly different world. Because the problem with those coroutines is you can see it actually even clearer here that, hey, you wanted to return something from this run internal and it needs to be enumerable again. It cannot be just the integer, right? It needs to be the enumerator. You need to go with all this bookkeeping, handling, transformations, yada, yada. I want to have an async where I can return anything and I don't need to care about that stuff. How do I do that? And this is how it comes. So now what we are going to do is we are going to use fibers. So to recap, we have this operating system level thread, which is basically a single thread provided to us by the operating system. And on top of that, we build green level threads. We build fibers. Each fiber is basically one async and await context, which will execute. So what we are doing is we have, again, some bookkeeping for doing the queuing and all that stuff, the same with yield as before. And now what we are doing is we submit two jobs to the execution logic. The first job is the regular run internal. You can see it's just a void method. It does run internal nested, which gets the task.delay. Then instead of calling await on this delay, instead of calling delay.wait, what we do is we do the magic wait. And this is the method we all wanted to have. This is the method which just stops the method, waits for the result, but allows everything else to carry on. How is this implemented? We'll have three fibers in this application. First fiber, so the first green thread is the green thread which is running this pumping inside the queue. So we get the message from the queue indicating, hey, there is some work to be done. And what we do next is we just switch to this thread. So we do the context switch to the other fiber. We tell the operating system, hey, I'm fiber number 0, I'm done. You can carry on with executing this other fiber, okay? So at this point, the fiber number 0 is basically stopped here, like paused entirely, and then fiber number 1 is being executed. It goes on and on until it calls magic.wait. And in magic.wait, what we do is we basically schedule a continuation to schedule fibers again, but more importantly, we ask the operating system, hey, I'm done. You can go to fiber 0. So there is this fiber 0, which goes through the queue, gets the messages, and then tells the OS, hey, go to fiber 1 to do this method. When this method on fiber 1 wants to await for something, it tells the OS, hey, I'm done, go to fiber 0. Okay? And then there is continuation on this task, which when it's done, so when we are done waiting for the delay or whatever else, we add this fiber to the queue indicating that, hey, this fiber is ready to be carried on again. So then fiber number 0 will pick it up from the queue and tell the OS, hey, I'm done, go to fiber 1. And on fiber 2, what we do is on fiber 2, we just submit the side job. Okay, so this is the important thing, that we just submit the side job which is here. Okay, and now to see this in output, you can see that, hey, we do have this running as expected. So we have, again, sleeping for 2 seconds, okay, and we have the side job being interjected somewhere in between. So this is what we can do with fibers. Now, how do we implement that? The part of the queuing here, you already know. There were some queues with keyword. The other part which we need to have is we need to have basically some, I use C++ CLI to basically call the WinAPI methods, right? So the only thing we need to do is we need to be able to call the switch to fiber from the WinAPI, delete fiber, and there is convert thread to fiber. And that's all. If you have this, you can actually go with the implementation of the async and await on top of green level threads. And this is exactly what Java Project Loom does. So instead of using these coroutine transformations, we just go with green threads on top of the OS threads. So the advantages of this, well, some of them are actually strikingly clear. There is no more task. You can just return void. You don't need to rewrite all your synchronous code to async, to have async all the way down, configure await all the way up, all the stuff. The only thing you need to do is you just do the delay dot magic wait. That's it. But that's not the end of the story. You remember this slide when I was pointing out three most important parts of async and await. First was coroutine transformation, okay? So this is covered. We got that covered. The other part was service locator, okay? Service locator for orchestrating the continuations. What we are going to do now is we are going to change the service locator thingy. And let me just tweak the code because it's quite a lot of code changes now. So let's run it. And now what we are going to do is we would like to use monad-like approach. For those of you who were sleeping for the last decade and not reading yet another post explaining what the monad is, this is not a monad. Just telling you. What we are going to do instead, if we are just wrapping this thing in a monad-like structure. So don't play tricks on that, it's not a monad. However, what is important is we would like to have an execution environment and we would like to have two different builders for two different monads. So basically a monad is a box with something inside. And this box takes care of how to deal with that thing inside. So we will have two different boxes. One of them being ID builder, like ID box, which is identity. And the other box is asynchronous box. And now comes the thing. Instead of doing anything with returning values directly, now we want to do actually take a step back and put everything into those boxes. So whenever we are dealing with the values, we are not doing them linearly with await or linear code, but we are more going with an approach of continue with on a task, okay? So we have this box, and instead of using continue with, we use the map function. We name it map. So we have a value, so we have something which is awaitable or sleepable here, and it's inside this box, and then when it's done sleeping, we have continue with, so it does something with the value, okay? So we wrap this thingy here. Now, the important thing is we have two different builders for that. So we run this application first with the asynchronous builder using async box. And when we run it, we get the expected output, right? So we have the sleeping for 2 seconds in between. And we also have this side job being introduced, interjected somewhere, okay? However, now the thing is, we can replace this box because we are using the factory, which is not located by a service locator. It is provided. We can just change it to something like this. So we pass it as a parameter to the execution context we are dealing with. And if we now change the asynchronous builder to the synchronous one, you can see that the side job was introduced at the very end because it was waiting for the previous part to finish. Meaning that just by changing this thingy here at the top of the application, like in your dependency injection container or whatever, you can control how the asynchronicity is being executed. You can control all the threading, anything around. You do not need to touch the code, the business logic, which is there. Okay, so this is great. That's the second thingy. But the third thingy, which we want to fix here, which we really don't like, is, hey, we took the step back and now we are wrapping everything inside this box. Okay, that's terrible. Let's get rid of that. And the last part, which we are going to do, is we address this third cornerstone of the async programming, which was that statically bound promise factories. So now, instead of using those boxes directly, what we are going to do is we are going to use them in some more dynamic way, thanks to, again, something similar to higher kinded type. So what we are going to do is a higher kinded type is a generic method which is being generic not on the input type, but the output type. Like you have IEnumerable of t, that's a regular generic. But you could have t of integer. That's a higher kinded type, meaning that the kind of the generic part is outside. Something which C# does not provide for you directly. You can emulate that with various transformations again, but we are going this approach. So now what we are going to do is We are going to have this run internal method, run internal nested. Again, they are like regular methods. No tasks around, no boxes, no continue with, no map. The only thing which it does is it gets this type parameter t, like generic parameter. And this generic parameter is of some builder, yada yada, just to get the call compiled. And then you see that we are calling task delay like in this way, delay of t. We don't care what this t was, okay? But we are just passing it through. And again, the idea is, if we do it this way, we can control it from the very top. So see, we can again get the 2-second sleep as needed. We can get the side job interjected in between, but just by changing this one little thingy, like this one parameter, generic parameter from asynchronous box to synchronous box, what we get now is we get that the side job is executed synchronously at the very end. So this is what we can do now. And you can see that by doing all those different transformations, we ended up with code which is colorless. There is no task around here. No task, no value task. If Microsoft introduces yet another Magicium task, you don't care. You don't need to rewrite all your code base anymore. You can control whether it's synchronous or not. You can change the synchronous mechanism. You can change the number of threads, thread pools, whatever you wish, without touching your business code. You control the synchronous parts directly in a place where they are executed, because nothing stops you from calling this method once with ID builder and the other time with asynchronous builder. So you can change it in runtime dynamically the way you wish. Important thing is, because it's a generic parameter and this builder thingy is, those monads can be introduced by the compiler, meaning that if you do have those builders, you could go with structures, meaning that your compiler would understand that those things can be heavily optimized. There would be no need for you to introduce value task anymore or anything like this, because compiler would just get rid of the allocations for you, and that's it. So you don't need to change your business code anymore. You don't need to do any code rewriting into async and await, async all the way up, configure await false all the way down, or whatever way it was. You don't need to change your methods. You don't need to deal with synchronization context and deadlocks, nothing like this. The only thing you do is you can just have it here with the green level threads. And this is what Project Loom does. Obviously, your compiler could hide those T parameters from you, and that's done. So, being all of that said, we can wrap up this talk. So we can see that coroutines, even though they give us this very nice experience of async and await, they generally give or bring quite a lot of overhead, which we can get rid of by using completely different approach. We don't need to use global state anymore. We don't need to use colorful functions. We don't need to pass tasks around from here and there. We could go with something completely different based on green level threads or whatever, and it would work exactly the same way and could be, as Java suggests, way more performant. Being all of that said, it's time for Q&A. So this QR code points you to the slide deck, or actually to my blog, to the blog with the slides and a couple more materials. And at the very end of this slide deck, there are more references for you, like books, blog links, etc., etc. Feel free to take a look at them. And that's it. If you have any questions now, is a perfect time to ask them. There is one, yes. Okay, so the question is, why isn't this, what we did here, why isn't that implemented in the operating system in the very first place? And that's actually a very good very good question. On one hand, we do not want to have these things in the OS itself, because then, well, .NET wants to support multiple platforms now. So having that implemented in Windows only would mean that we need to implement this in Linux by ourselves or whatever, or need to have exactly the same implementation in Linux. But the other thing is is that those things were not implemented in this way, like why they were not implemented in the .NET runtime, why they were implemented in the C# compiler. The answer is because it's a choice to be made. Basically, it's a decision to be made. So .NET Platform decided that they do not want to mess with the .NET runtime to support all of that. They wanted to mess with the C# compiler. That's why they implemented it in this way. They also didn't want to mess with the operating system to add all those stuff. Java took a different route. They decided to change all the platform under the hood, so all languages can benefit from there. You do not have async and await in VB.NET, right? Because it's not implemented in the compiler. But if you do have multiple languages running on Java, then in theory, any of them can use all the benefits here. Now, when it comes to the memory consumption, etc., generally, if you are implementing things in the operating system, then you need to deal with the kernel switch, context switch to the kernel mode, which is always heavy, always very, very expensive, and generally you do not want to do that. And you cannot get rid of that because of security and all the other implications. So generally, while it is beneficial if you have those things provided for you, it's actually very heavy for the OS itself or the dependent platforms to implement them. And that's why you might want to consider implementing them by yourself. Any other questions? Yep. Okay, so the question is, I did convert the thread to Fiber, and the question is, how does it integrate with other things which can be around, like dispatch context in WPF, web requests, etc., etc. The answer is, Microsoft, or actually the .NET Platform, they did consider using fibers at some point. They were supporting that in SQL Server and its some CLR version, but at some point that explicitly dropped that support because fibers do not give you, like, make your multi-threading code a little tricky, because all your synchronization primitives, like mutexes, semaphores, yada yada, they are always tied to the thread. So now, if you have two green threads running on top of one OS thread, then if one green thread takes a lock, then the other green thread has this lock acquired as well. So that's why they wanted to drop it, because support in multiple platforms, in pinvoke context, etc., was tricky. And they explicitly banned it. Not that they are not supporting fibers, they are explicitly unsupporting them. Okay. So how does it integrate with WPF, etc.? This code does not, because it's just a proof of concept. You could go with the places when I'm doing those boxes like ID builder, async builder, you could introduce all your logic there. It could be integrated. This is why it took Java so long to implement this, because they had to take care of all those things. But the other question is, okay, I mentioned that synchronization primitives are broken with green threads, let's say. But is it any different with async and await? And the answer is, it is not. If you do take a lock in your asynchronous method, then it is not migrating to the other thread you may be running your continuation on. If you do use async and await, you need to forget about all the regular synchronization primitives. So the thing is, Microsoft didn't want to drop those primitives by moving to fibers, but they effectively dropped them the same way by moving to async and await. And now there is no code which is not async enabled in C#, right? There was this very long transition period, like 5 years, when we were rewriting all the methods from regular to task, async, await, yada, yada. Now everything is async and await. So you cannot use your lock primitives anymore. Even if you try using lock construct in like async method, it may yell that you cannot await inside the lock, right? Because it won't migrate to the other thingy. So those are exactly the same things, the same issues for which Microsoft didn't want to go with fibers, but effectively went with them when introducing async and await. So to sum up, this gives you a lot of troubles when it goes to going with green threads, but you have those issues the same with async and await. And I refer you to my other talk, async biggest C# mistake. You can find it on YouTube explaining all those issues. But generally, you do not have any more troubles per my understanding. There could be some edge cases, obviously, but generally this is equivalent when it comes to how many troubles you get. And if you can integrate this with WPF dispatcher or whatever else, the answer is yes. You just need to write a little more or sometimes way more code doing the job under the hood, but it was done anyway for async and await. If you start decompiling async and await, you will see tons of different synchronization contexts for WPF, for Blazor, for old ASP.NET, for new ASP.NET. You will find that code being written anyway. It's just we would need to write this code having different mechanism in mind. That's it. The code needs to be written anyway. Any other questions? Okay, I don't see any of them. If you had any other questions, feel free to ask them after the presentation. Couple of references for you. You can find them in the slide deck. And because we are out of time, being all of that said, I think it's time to call it a day. Thank you for attending this talk. Hope you liked it. Hope you enjoyed. Thank you.